তাহলে স্টার্টই করি নাকি? হ্যালো? হ্যালো?
Yes, sir.
তাহলে স্টার্টই করি নাকি? আর তো কেউ
Mhm.
আসবে না? হ্যাঁ, ঠিক আছে, দেখি দাঁড়াও। আগের দিন কি হয়েছিল একটু দেখে নিই। আগের দিন কি হয়েছিল একটু রিক্যাপ করে নিই। বেসিক লজ, ট্রান্সফর্মার অপারেটিং প্রিন্সিপল।
Sir,
হ্যাঁ, বলো।
sir, just a humble request. If you could speak in English, it would be better.
হ্যাঁ, ঠিক আছে, ঠিক আছে, ঠিক আছে, ঠিক আছে, দাঁড়াও। ওয়েট। কি এলো? Previous day, we are discussing about transformers. This is the transformer. We have discussed it. What's up? Have you seen the mouse pointer? Have you seen the mouse pointer?
Yes, sir.
This is the simple transformers, but not actually it is. It has two limbs. One is here, another is here. One winding is in this limb. It is known as the primary, and another one is here. It is known as the secondary. And if you apply voltage here, then what will happen? This is explained in the phasor diagram. The voltage in sinusoidal nature. So this is the voltage which is sinusoidal in nature. If you apply here, then what will happen? EMF will induced here, which is E1. Which is E1. It is actually back EMF. It may be known as the back EMF. And the phase of the EMF E1 is just reverse than that of V1, which is seen here. Okay. If we apply voltage here, then current will flow. This is the current which is lagging in nature. Then the V1 lagging in nature. It creates a flux. Flux will circulate here. The closed path is here. The flux will flow in these directions. Okay. The flux is associated with this secondary coil. And if it is associated with secondary coil, there is d phi dt is there. So EMF will be induced here, which is E2. And E2 and E1 are in same phase, which is drawn here. Okay. So this is the phasor diagram. This is the directions of phi, which is the flux. Same with the direction of current. Both are in same phase. This is the voltage V1 and EMF E1 is here. EMF E1 and E2 are in same phase, which is shown here. Just come to the next page. What happens? This was the EMF equations which has been previously, that is in previous class it is explained. The flux phi equal to phi m sin omega t, sinusoidal in nature. Phi m is the maximum flux. U1 equal to minus n1 d phi dt. Okay, according to Faraday's law, and it comes into here minus omega n1 d phi cos omega t. Okay, this is the E1m is the maximum value. Is the instantaneous value. And it is the maximum value. It is the maximum value. Okay, this is the waveform, sinusoidal waveform maximum value, and this is the RMS value. You know, maximum value divided by square root, it will give you RMS value. So this is the EMF equation of transformer, which is E equal to 4.44 phi F N1 phi M. Okay, and obviously this is the 4.44. It comes due to the sinusoidal voltage only. If we apply different shape of the voltage, then it will be different. Note that 4.44 is due to the sinusoidal voltage only. Ultimately, we proved that E2 by E1 equal to N2 by N1 equal to K. Okay, E2 by E1 equal to N2 by N1 equal to K. K is the trans ratio. From here, the three case has been discussed. Case 1 is for step up transformer. Step down is case 2 is for step down transformers, and case 3 is for 1:1, that is isolation transformers. All are discussed in previous class. Now we shall discuss the new thing. What is this? The transformer with losses but no magnetic leakage.
স্যার স্যার স্যার
Yes.
সরি টু ডিস্টার্ব আপনাকে
হ্যাঁ।
একটু
হ্যাঁ বলো।
বলছি স্যার ইজ দের এনি রেকর্ড অপশন আপনাকে কোনো রেকর্ড অপশন দেখাচ্ছে কি তাহলে একটু রেকর্ড করতেন এটা তাহলে আমাদের একটু সুবিধা হতো ফর ফিউচার রেফারেন্স
আসলে আমি এটা জানি না আসলে।
না স্যার গুগল মিটটা আপনার কোথাও রেকর্ড অপশন দেখাচ্ছে কি বা আমারটা অ্যাকচুয়ালি দেখাচ্ছে না রেকর্ড অপশনটাতে তো
আচ্ছা
তাই জন্য নাহলে আমি রেকর্ড করে নিতাম
আচ্ছা গুগল মিট দাঁড়াও দেখি দাঁড়াও এখানে আছে কি?
যদি দেখায় আপনার কোনো না হলে
না আমি
ছেড়ে দিন।
জানি না আসলে দাঁড়াও। আচ্ছা একটু দাঁড়াও আমি দেখি। হ্যালো হ্যালো।
Yes, sir.
হ্যাঁ এটা বোধহয় এটা ফ্রি ভার্সন বলে বোধহয় নেই মনে হচ্ছে জানো তো। Probably it is free version, that's why it has no record facility probably.
আচ্ছা আচ্ছা ওকে স্যার
হ্যাঁ।
তাহলে স্যার একটা এই পিডিএফটা আমাদেরকে একটু তাহলে পাঠিয়ে দেবেন
দেবো তোমাকে সব দেবো চিন্তা নেই।
ওকে স্যার থ্যাংক ইউ
সে সব দেবো। আচ্ছা now come to the topic transformer with the losses but no magnetic leakage. You know the loss is due to the copper loss. Okay, there is a resistance. If current is flowing there, then ohmic loss will be there, which is I square R. Consider the transformer which has losses. Okay, losses but no magnetic leakage. Loss may be two types, you know. One is the core loss, which consists of copper, which consists of eddy current loss and hysteresis loss, and another is the copper loss. Suppose the transformer is in no load, then if you apply voltage here in primary side, then flux will flow, and since flux is flow, then core loss will be there. Okay, but what about copper loss? Since secondary is not connected to any load, so there will be no copper loss in secondary side, but in primary side the exciting current only flows. That's why there is some copper loss in primary side. So we can gist this. The two loss may be there, two loss is there. One is the core loss, another is the copper loss. Since it is no load, their major loss is the core loss, and the minimum loss is the copper loss, which occurs in the primary side only, not in secondary side. Suppose consider the transformers which was seen previously, not connected with load. Then no load input power equal to W0 equal to V1 I0 cos phi 0. V1 is the applied voltage, I0 is the no load current or exciting current. Okay. and cos phi is the power factor. Obviously, phi 0 is the angle between voltage and current, which is shown in the phasor diagram. Okay. So the exciting current, that is no load current, it has two components. One is the active or working or loss component, which is denoted by I mu, and it is equal to I0 cos phi 0. You know that. And there is the magnetizing component, which is IW equal to IW or I omega equal to I0 sine omega t. This is the active power, and this is reactive power. That's why it is known as the loss active component, and it is reactive component, and it creates or generates flux, and it is known as the magnetizing component. Obviously, you know the simple relations: I0 equal to square root of I mu square plus I omega square. Okay, all are seen in the phasor diagram. Okay, we can explain the phasor diagram. This is the applied voltage V. If you apply voltage V, then current will flow, which is I0. Okay, if it is purely inductive circuit, then theta will be 90 degree. Okay, but here we consider some loss here, that is some resistance. That's why the angle is not 90 degree. Okay, which is theta here. It has two components. One is here, another is here. It is IW. That is sine part, and this is the cos part. This is your loss component. This is your magnetizing component. Okay, and E1 is just refers with the V1. Okay, and E1 and E2 are in same phase. এই কিছু বোঝা যাচ্ছে গো? It is understand?
স্যার কিন্তু ওখানে আই ডাব্লিউ হবে না আই মিউ হবে
এটা
V1 এর
আই
সাইডে।
মিউ হবে সরি আই মিউ হবে। আচ্ছা, আমি কারেক্ট করবো আবার।
স্যার আমার একটা কোয়েশ্চেন আছে এখানে।
বলো।
আগের হ্যাঁ স্যার, এখানে মানে নো লোড পাওয়ার ইনপুট পাওয়ারে যে W0 তে লেখা আছে V1 I0 cos phi 0, বাট
হ্যাঁ।
এটা তো V1 I0
এটা ভুল আছে।
sin phi 0 হবে।
কেন হবে?
স্যার মানে ইনপুট এখানে পুরোটাই আমি লস, এখানে ইনপুট পাওয়ার বলতে তো মানে অ্যাক্টিভ পাওয়ারকেই বোঝানো হচ্ছে।
তো দিস ইজ অ্যাক্টিভ পাওয়ার। ইজ ইট অ্যাক্টিভ পাওয়ার? ইয়েস অর নো?
না, এটা তো অ্যাক্টিভ পাওয়ার হচ্ছে না এখানে।
কেন বলছো?
স্যার এখানে মানে অ্যাকচুয়ালি
না, দিস ইজ অ্যাক্টিভ পাওয়ার। কস পোরশন ইজ দ্য অ্যাক্টিভ পাওয়ার। এটা তো
বাট
সবাই
স্যার
জানে।
না স্যার, এখানে phi 0 আর থিটা তো আলাদা অ্যাঙ্গেল। থিটা যেটা ওটা তো phi 0 না, এটা থিটা হলে ঠিক ছিল, মানে V1 I0 cos থিটা লিখলে এটা অ্যাক্টিভ পাওয়ারই হতো, কিন্তু এখানে তো cos phi 0 আছে, আর phi 0টা এখানে হিস্টেরেসিস অ্যাঙ্গেল অফ অ্যাডভান্স, মানে I0 আর I মিউ এর মাঝখানের কোণটা হচ্ছে অ্যাকচুয়ালি phi 0।
না ঠিক আছে, বুঝতে পারছি। আচ্ছা, তুমি বলছো কি
মানে স্যার এখানে যদি phi 0 জায়গাটা থিটা থাকতো তাহলে ঠিকই ছিল, এটা অ্যাক্টিভ পাওয়ারই হতো।
আচ্ছা, তুমি বলছো যে এইটা থিটা হলে
থিটা হলে ঠিক ছিল, থিটা হলে ঠিক ছিল, কিন্তু phi 0 মানে তো থিটা মানে 90 ডিগ্রি মাইনাস থিটা, phi 0 মানে।
এখানে একটা গন্ডগোল আছে। আচ্ছা দাঁড়াও। আচ্ছা, এটা আমি ঠিক করে দেবো, অ্যাসিউম করে যাও। ঠিক আছে, এটা অ্যাসিউম করে আমি ঠিক করে দেবো। আচ্ছা, তাহলে এই পর্যন্ত মোটামুটি ধরে নিচ্ছি ঠিক আছে, তাই তো? শুধু এইটা ডিসপুট আছে বলছে, তাই তো?
হ্যাঁ স্যার,
এটা ডিসপুট আছে, ঠিক করে দেবো।
ঠিক আছে।
আচ্ছা, next come to this slide, transformer on load. Up to this we have considered transformer with no load. Now you connect with the load. Okay, you know this figure, okay, which is no load. Now connect the load here. What will happen? The flux phi 1 is circulated in this way, in this path. If you connect load here, then I2 will flow due to the induced EMF E2 here. Okay, if I2 is flows, then it will create flux which is in opposition with phi 1. okay, which is in opposition is phi 1. Suppose since the flux decreases, the input current will increase, which is denoted by I2 dash, which is denoted by I2 dash. Now, the current in secondary is I2, in primary is I0 plus I2 dash, which is equal to I1. So the current I1 equal to I0 plus I2 dash. That's all are written here. Phi 2 equal to phi 2 dot, that is Ni ampere turn. Phi 2 equal to phi 2 dot. From here we can write into I2 equal to N1 I2 dash. Okay, since phi 1 equal to phi 2 dash. From here we get I2 dash equal to K into IT. So if current flow in secondary is I2, then its reflections will be I2 dash, which is equal to K into I2. K is the trans ratio. Phi 1 is slightly greater than phi 2. If we neglect I0 in compared with I2 dash, then we can write these equations. Okay, we can write this equation, that is the canvas. কি করে যায়, আচ্ছা, which is equal to N1 I2 dash equal to, এটা পড়ে নিতে হচ্ছে, ultimate what happens, I2 dash by I1 equal to I1 by I2 equal to N2 by N1 equal to K. Okay, so if you apply voltage here, then this will happen. Once again we can repeat this, this is the no load conditions. If you apply the load, then current will flow I2, due to which another flux phi 2 will develop, which is in opposition with phi 1. So resulting flux will decrease. If resulting flux decrease, then back EMF will decrease. Okay, since I equal to V minus back EMF divided by R or Z, since back EMF is reduced, I2 will increase. What amount of I2 will increase? Which is equal to I2 dash. Okay, which is equal to I2 dash. And the what is I2 dash? I2 dash equal to K into I2. Okay. Achha. If we neglect I0, then we can write this expression only. Now we can explain this with the help of phasor diagram. This is the no load conditions. Okay, this is the no load conditions. Directions of V1, directions of phi. This is I0. This is I0. It is I2, and reflection is I2 dash. This will be I2 dash. Okay, this will be I2 dash, and I2 dash plus I0 equal to I1. So this is primary current, and this is secondary current. Okay. These are the next portions. These are the next portions. Since there is some angle, there is resistance, there is resistance, inductance, etc. So there is an angle between V and I2 dash. Okay, in this case, since it is lagging actually, I0 and I2 dash, it will give you the I1. Okay, so this is the phasor diagram. The last one is, if you consider I0 is negligible and if you omit this, then I1 equal to I2 dash. Okay, and in this case, this last relation is valid. Which relations? This relation is valid. Okay, so this is your phasor diagram. All are here. You can just study this. The first case, if you just connect load here, if you consider resistance here, then it comes. If you omit I0, since it is negligible, actually it is 2 to 3% of the full load current for ordinary transformers. So we can draw this phasor diagram. Now consider transformer on load. Consider transformer on load. Here we consider only resistance. There is no reactance, etc. Okay, this is the figure which consists of two resistance R1 in primary side and R2 in secondary side. Apply voltage here V1, induced EMF will be E1. So we can write this. We can write these equations, the second equations. Okay, E1 equal to V1 minus I1 arrange the drop. Now come to the secondary side. Here the voltage induced is E2 and load voltage is V2 suppose. Then we can write this expression. Okay, this is your phasor diagram. This is for resistive load. This is for resistive load. You study this. Flux phi, voltage V1, flux phi, EMF E1 actually in this side. In this side, for drawing phasor diagram, we have shifted in these directions, in the upper directions, which is I1, E1. The expression, from these expressions, we can write this E1 plus I1 R1 equal to V1. That is V1 minus I1 R1 equal to E1, which is the second equations. Okay. And I think all are accessible to you. This is for lagging power factor load. For lagging power factor load, and this is for leading power factor load. Okay. Since transformer is on load, load may be three types. One may be resistive load, another are one inductive load and capacitive load. And these are three phasor diagrams. This is for resistive load, that is power factor unity. This is for inductive load, power factor lagging, and this is for capacitive load, power factor is leading. Here, the voltage, the current I1 lags V1. Here, the current I1 leads V1. Okay. Now come to the equivalent resistance. কেন এটা লাগবে? For the simply for calculating the any problem or for getting the performance or starting performance, it is required. So it is the equivalent resistance. Transformers is there, two windings are there in two limbs, one is primary and secondary. These are not connected electrically, but they are connected magnetically. Okay, and in this case we can find out the equivalent resistance. Let R1 is the resistance in primary circuit and R2 is the resistance in the secondary circuit. What is the drawbacks of resistance in coil? In coil, there is a copper loss, which is I square loss. The copper loss is secondary if is I2 dash R2. R2 is the resistance in the copper loss in the secondary side. Our aim is to convert or transfer the R2 in primary side. Okay, then it will be easy for calculations. This loss is supplied by I1. Okay, the secondary loss is I2 dash by I2 square R2, and this loss will be supplied by I1. Hence, if R2 dash is the equivalent resistance of primary, which would have to cause the same loss as R2 in the secondary, then we can write these expressions. R1 square R2 dash equal to R2 square R2, or R2 dash equal to I2 by I1 square R2. Now, if we neglect current I0, then we can write I2 by I1 equal to 1 by K. Hence, R2 dash equal to R2 by K square. R2 by K square. That is, if the resistance R2 is transferred into primary side, then it is equal to R2 dash. What is R2 dash? It is equal to R2 by K square. Okay. From here, we can write this. We can write this. The resistance R1 plus R2 dash equal to R1 plus R2 by K square is known as the equivalent of effective resistance in transformers as referred to primary and may be designated at R01. Here two coils are there. One is primary and secondary. If we consider the secondary winding is ideal, that is there is no resistance, and it is the resistance R2, it is the case, the resistance R2 from secondary side is referred to the primary side. So this is the total resistance in the primary side. Okay, and it is known as the equivalent resistance referred to the primary side and designated by R01. So R01 equal to R1 plus R2 dash equal to R1 plus R2 by K square. So this is the equivalent resistance. This is the equivalent resistance. It is referred to the primary side. In similar way, we can transfer into this in the secondary side. And if we transfer in secondary side, then the resistance R20 equal to R2 plus R1 dash. So clearly, this R1 is transferred into the secondary side. Okay, so three cases are there. One is transformers. Two resistors are there in primary side and secondary side. And next one is all the resistance transferred in the primary side. And if you transfer the resistance from secondary side to primary side, then this will be the R01 will be the equivalent resistance. And note that the performance, if you change this, the performance will not hamper. This is for easy calculation. Okay. Similarly, we can change, transfers all the resistance in the secondary side. Okay. Any one can be taken for the tackling any problem or solving any problem. Next, come to the magnetic leakage. Magnetic leakage. Up to this, we have considered only the winding resistance, but not any leakage. What is this? Consider this figure. The voltage V1 is applied here. Voltage V1 is applied in primary side. If we apply voltage V1 here, then I1 will flow. I1 will flow. Since I1 flows, the flux will generate, which is phi 1. So theoretically, all the flux will circulate, will travel through this path. Okay, because it is a low reluctance path. But practically, if we see, then there is some leakage. What is the leakage? It completes magnetic circuit through air. Yeah. What is this? The normal path is this. This is the normal path. But a portions may complete their path through the air, which is suppose phi L1. Okay. Similarly, if current flow in secondary side I2, then there may be some leakage flux phi L2. Note that this phi L2 is not connected with this circuit, or this phi 1 is not connected with this circuit. So this will not induce any EMF here, or this will not induce EMF here. Okay, all are written here. All are written here. If the current I1 is flowing the primary side and EMF induced is EL1, then X1 equal to EL1 by I1. So X1 is known as the leakage reactance. Similarly, for secondary side, X2 is the leakage reactance. Actually, there is no physical existence of this leakage reactance. Okay, if we consider this is ideal transformers, so for making it practical transformers, we can connect here X1 and here X2. Okay, so this is the practical transformers, this is ideal transformers, and the total is the practical transformers. Once again, if there is no existence of any inductance or X1 or X2, we just consider to represent the leakage reactance actually. So if we consider the practical transformers, it consists of two coils, primary and secondary, along with resistance and reactance. Okay, this reactance is known as the leakage reactance. Now the equivalent circuit. This is your transformers equivalent resistance actually. Equivalent, এটা আবার কোত্থেকে এলো? নিচে পড়ে গেছে বলে। This is your practical transformers consisting of resistance and leakage reactance. It is represented in the figure. Z1 is the input impedance square root of R1 square plus X1 square. Similarly, Z2 secondary impedance, which is equal to the square root of R2 square plus X2 square. And the following are to the voltage equations. V1, applied voltage V1 equal to U1 plus I1 R1 plus JX1. Okay, you know J, it is the operator which when rotates with the quantity, it multiplies by 90 degree. And the last two is the voltage equations for primary and secondary respectively. Now come to the phasor diagram. These are the phasor diagram corresponding to the practical transformer, which consists of resistance and reactance. Three figures are there. First one is for unity power factor load. Second one is for lagging power factor load. Third one is for leading power factor load. Now come here. Okay, we have explained the two equations previously. Now come to this figure. This is your V1. Where is V1? This is your V1 support. This is your V1 support. If we applied V1, then what will happen? I0 will flow. It has two components, I mu and I omega. If you connect load, then I2 will flow. Then I2 will flow in these directions. I2 will flow in these directions. Since load is connected, then reflection will be in primary side, which is I2 dash. Here it is I2 dash. And obviously, I0 plus I2 dash will give you I1, which is the phasor sum I1. Okay. In primary side, E1 is there, back EMF. If you add the three voltage, that is E1, I1 R1 and I1 X1, then it will give you V1. Okay. This is E1, this is I1 R1, same with the direction is the I1. Okay. I1 X1, its direction is the 90 degree with I1 R1 is 90 degree. Okay. If you add all three, that is E1, resistive drop, reactive drop, it will give you V1, which is the applied voltage. Okay, this is the impedance triangle. This is the R, X, and it is Z. Impedance triangle. Okay, so it is clear. In the secondary side, this is the E2. In secondary side, if we applied V, resistive drop and reactive drop, it will give you the induced EMF. This is V2, I2, R2, same with V2. Why same with V2? Since it is unity power factor load. And this is the reactive, which is 90 degree apart. So all sum of the V2, I2, R2 and I2, X2, it will give you E2. So it is clear. Now come here. It is the inductive circuit. Similar. V1, this is V1, sum of the E1, I1 R1 and I1 X1. Okay. In secondary side, it is E2. Actually, it is V2. This is V2. I2 R2. Actually, there is some angle. This is parallel with this. And last one is the I1 X1, I2 X2. And the sum V2, I2 R2 and I2 X2, it will give you E2. Similarly for leading power factor load. This is self-explanatory, just study it. So this is the vector diagram, phasor diagram for three loads: resistive load, inductive load, and capacitive load. Transformer with resistance and leakage reactance. Okay, so the equivalent impedance is here. This is equivalent impedance. If you consider resistance and reactance both, then this is the equivalent impedance. This is Z01, that is impedance with refer to the primary side. It consists of two portions, R01 equivalent resistance, and this is X01 equivalent reactance. R01 consists of two parts, R1 plus R2 dash. X01 consists of two parts, X1 plus X2 dash, and this is Z01. This is your Z01. Similarly, this figure shows all the resistance and reactance, that is impedance, are referred in the secondary side. And these are the explanations. Z20 consists of two portions, R02, X02. This is consists of two portions, R2 plus R1 dash, and X01 consists of two things, X2 plus X1 dash. Okay, these are explained already. Now come to the simplified phasor diagram. Simplified phasor diagram. Okay, this is for calculating regulation, etc., etc. In this figure, it is for it shows the simplified phasor diagram. You know the phasor diagram which is explained in previous pages. Here, this suppose since it is simplified, so we can we neglect I0 and it is omit. Why we can omit this? This is 2 to 3% of the full load current, or I1, like this, and that's why we neglect this. Next, all the voltage on the primary sides have been transferred into secondary. Okay, these voltage, these are the primary sides voltages and voltages drops, and this is the secondary side. All the primary sides quantities are transferred into the secondary. Here the upper part of the diagram has been rotated to 180 degree. Okay, which has been shown in the figure. 180 degree rotation is there. Note that voltage or voltage drops has been multiplied by transformation ratio K. Okay, you know there is a relationship between primary side quantities and secondary quantities, and these are connected by the factors K, which is the transformation ratio. If we transfer the primary sides voltage or voltage drop in secondary sides, then it will be multiplied by K, and using this diagram is drawn. Okay, go to the next page. Next page. Okay, all upper portions is transferred in the lower portions. This is V2 secondary side, V2 I2, V2 added with I2 R2 plus I2 X2. Okay, it will give you E2. Actually, it will be E2. Okay, আর কি আছে? This is I1 R1, I2 R2, this is a primary voltage. This is primary voltage. Actually, primary voltage is V1. If you transfer in the secondary side, it will be multiplied by K. Okay, so this is the equivalent primary voltage referred to the secondary. Okay, it is the resultant of all the quantities, that is V2, I2 R2, I2 X2, K into I1 R1, K into I1 X1. Okay, this is more simplified. This is more simplified. Resistive components are added. This resistive part and this resistive part, which are added, which is equal to this. This is a reactive part. Two reactive parts are added. Similar with this first one, that is V2 plus all the resistive drop plus all the reactive drops will give you the equivalent primary voltage. This is for reactive. This is for inductive load. Similarly, this is for resistive load, and this is for capacitive load. Now come to the voltage drop portions. What happens? The transformers is used for transferring for supplying load. Suppose there is a transformers. If you connect a load here, it is necessary that voltage will not drop. Okay, so this is known as actually the regulations, which will be covered in next class. For a good transformers, the regulations will be low, that is 1 to 2% like this. So for calculating regulations, we have to calculate the voltage drop. That's why this is the topic, voltage drop in a transformers. It is actually approximate voltage drop. After this, we will calculate the exact voltage drop. Okay, it is written that when a transformer is at no load, then V1 is approximately equal to E1. Okay, since resistance and leakage reactance in the winding is very low, hence I2 equal to KE1 equal to KV1. Okay, you can write this if you consider only the resistance and reactance as very low. Also E20 equal to 0 V2. V2 indicates the secondary voltage, and this is for no load actually. Where this is the secondary terminal voltage on no load. Hence, no load terminal voltage is K into V1. Okay, the secondary voltage on no load is V2. So this is the figure. Okay, this is the voltage drop. This is the secondary voltage V2. Secondary voltage V2, and equivalent secondary voltage is 0 V2, which is equal to K into V1. So voltage drop is A into M. A into M actually voltage drop. So if you apply load here, then voltage drop will be there, which is equal to A into M, which is approximately equal to A into N, because we are finding about approximate voltage drop. So approximate voltage drop is A into N. We have to calculate this. You have to calculate it. N can be resolved into two portions, AD and DN. You know, AD and DN. This is the AD portions, and this is the DN portions. AD equal to I2 R02 cos phi. Okay, it is clear from the figure. Similarly, DN equal to I2 X02 sin phi. One portions, and this is the another portion. So this is the approximate voltage drop. This is the value of approximate voltage drop for lagging power factor only. So it is the voltage drop for lagging power factor. Okay? Load may be leading or unity power factor. This is for lagging power factor. If we consider leading power factor load, then what will happen? For leading power factor load, it will be just negative. Go to previous page. It is positive. Okay, if you consider the leading power factor load, this will be negative, and other quantities are same. So the general approximate voltage drop will be this. This is the approximate voltage drop. For plus indicates for leading power, lagging power factor load, and minus indicates leading power factor load. So this is the general expression for approximate voltage drop. Obviously, you see there are two, etc. So this is for refer to the secondary side. It may be refer to the primary side. In this case, the two will be changed into 2. So this is the approximate voltage drop with respect to the secondary side, and this is for the primary side. Okay, plus sign indicates lagging power factor load, negative sign indicates leading power factor load. Now come to the voltage drop, percentage voltage drop in secondary side. Okay, this is the drop, and this is the no load voltage. So this is the percentage voltage drop. Okay, percentage. So you have to multiply it by 100. It consists of two parts. One is here, another is here. Okay, this is cosine term, and this is the sine term. We can write it this as VR, and this is Vx. Okay, what is VR? 100 into I2 R02 by 0 V2. It is the percentage resistive drop. Okay, similarly, Vx is the percentage reactive drop. So you have to remember these equations only for calculating for solving problem, etc., etc. So I think this page is clear to you. Now come to exact voltage drop. Up to this, we neglect the portion Nm. Nm, we find out only the value of An. Now our task is to find out the N into Nm, these portions. Okay, consider the right angle triangle OCN. What is OCN? OCN. Okay, from here we can write this NO square equal to OC square minus ON square. OC equal to A square minus B square, that is A plus B into A minus B. It is written here. Okay. Ultimate, just study this or scan this. However, ultimate, we get Nm equal to NO square by 2OC. That is NC equal to LC minus ALN equal to LC minus BD. This is vital. This page is vital. This is the NC. This is the NC. NC means this is NC. Okay. NM equal to these portions from trigonometric relations. Yeah, I think you know this. If it is circles, then this into the lower portion, this, it will happen 2 into this into this. Again, there is some approximations, but it is very, very negligibly small. However, we can write this expression, N equal to this. Now, for lagging power factor, voltage drop, the two portions will be there. One is ON, another is NM. These portions we have calculated. Hello?
স্যার বলছি আগের ভিডিওটাতে প্রেজেন্টেশনটা দেবেন
বলো বলো
আগে প্রেজেন্ট
আগের প্রেজেন্টেশন
আগেরটা
হুম
মানে প্রিভিয়াস পেজ।
হুম স্যার এখানে NO স্কয়ার ইকুয়ালস টু OC স্কয়ার মাইনাস ON স্কয়ার, স্যার এটা OC স্কয়ার মাইনাস CN স্কয়ার হয়ে যায় না?
হতে পারে, আমার ভুল থাকতে পারে। এগুলো মিনিমাম দেখে নিতে হবে, হ্যাঁ। NO স্কয়ার, হ্যাঁ, মানে NO স্কয়ার ওই দেখে নিও আর কি, ঠিক আছে।
So OC plus ON 2OC হচ্ছে।
দাঁড়ো, NO স্কয়ার OC স্কয়ার মাইনাস এটা NC, ইট উইল বি NC, তাই তো? It will be
Yes,
NC.
sir.
It will be NC. That is CN.
হ্যাঁ
CN. So it will be CN. তাই তো? It will be CN.
হ্যাঁ
It will be CN.
সেটাই।
It will be CN. তাই তো? তারপরে এসে যাবে।
হ্যাঁ তারপরে
এসে যাবে। ওইগুলো ভুল হয়েছে আর কি। এনিওয়ে, যাই হোক, ঠিক আছে।
ঠিক আছে। হ্যাঁ
ঠিক আছে, ভুল আছে, পরে ঠিক করতে হবে। ঠিক করতে হবে মানে ওই দেখে নিতে হবে, সব হয় নাকি? আচ্ছা, সো ইট ইজ ক্লিয়ার। So for lagging power factor load, this portion plus these portions, that is ON plus NM. Okay, it is correct. Is it correct? This portion is AN. This is NM. A response করো। Is it correct?
হ্যাঁ স্যার, মানে ওপরটা দেখে তো ওটাই হচ্ছে।
হ্যাঁ, উপরটা থেকে টাই আছে, ঠিকই আছে এটা, ঠিক আছে। Similarly, for leading power factor load, the last one, leading power factor load, this is plus, for leading it is minus. Okay, leading minus, and for lagging it is negative, for leading it is positive. Okay, so this is the voltage drop voltage drop for lagging power factor condition. This is for leading power factor condition. Now the general expression. Just put plus minus, and here minus plus. Okay, this plus and this minus is for lagging power factor load, naki ultota, and minus and plus this is for leading power factor load. Now come to the percentage voltage drop. Just multiplied by 100. Multiplied by 100. Okay. And like previous case, this is VR. That is I2 R2 R02 by V02 into 100 equal to VR. So it is VR cos phi plus minus Vx sin phi plus 1 by 200. Note that this is 1 by 200. Vx cos phi minus plus VR sin phi. So this is the exact voltage drop. This was the phasor diagram, simplified phasor diagram. From the simplified phasor diagram, we are calculating approximate voltage drop. This was the figure. Okay, so voltage drop is O into N. Okay, by calculating, we get this is the voltage drop. Okay, note that there is some positive sign. In next page, for lagging power factor load, the negative sign. General formula is, general expression is this, and obviously two are there, so that is the voltage drop referred to the secondary side. Similarly, voltage drop referred to the primary side, this one. Okay, and after a long, we get percentage voltage drop in secondary side referred to the secondary side, VR cos phi plus minus Vx sin phi. This is the general formula. Next, it was exact voltage drop. Up to this, we are neglecting the portion Nm. Here we will find the portion Nm only. Okay, there is some mistake here which will rectify after this. However, we get the voltage drop Nm, and total is the these portions and these portions, and this is your exact voltage drop for lagging power factor load, and this is the exact voltage drop for leading power factor load. This is the general expressions, and in short form you can write these expressions. Okay, this is the ultimate. We have discussing this. Now go to the next slide. Equivalent circuit. Equivalent circuit. Again, the first symbol, first circuit, first figure is for transformer. Obviously, it is ideal transformers. It is ideal transformers. If you connect resistance and reactance in primary and secondary side, it will give you the practical transformers. And this is your practical transformers. This is your practical transformers. So this is your practical transformers. The two coils are there only. Okay. If you connect the resistance, reactance, and resistance reactance, it will give you the practical transformers. Now, apply voltage V1. If you apply voltage V1, then current I1 will flow. Current I1 has two components. One is I0 and another is I2 dash. Okay. What is the purpose of I0? It will give you the magnetizing component, that is phi. It generates magnetizing flux phi, and the some copper loss. That is, it has two components. One is I omega and another is I mu. Okay, it will be mu. I mu. I mu passes through the x0 and I omega passes through r0. Okay, another portion is I2 dash. Actually, this is the magnetizing component, and it will give you the load current. Okay, which is nothing but reflections of the current I2. Okay, I think it is clear. Once again, there are two coils which is for practical ideal transformers. If you connect the lumped parameters R2, X2 and R1, X1, it will give you the practical transformers. Now, apply voltage V1, current flow I1. I1 has two components, I0 and I2 dash. I2 dash it comes due to the reflections of I2, and it supplies the load current, and this is the magnetizing current. It has two components. One is I mu, another is I0. Okay, and two parameters are there, X0 and R2. Okay, X0 and R2. X0 and R2. What is X0? What is X0? E1 by E1 by I mu. Okay, X0 equal to E1 by I mu. E1 is this voltage, the back EMF by induced voltage, E1 by I mu. Similarly, R0 equal to E1 by I omega. Okay, and ZL is the load impedance. This was secondary side. Secondary side, I2, R2, X2, and this is the load, induced voltage E2, load voltage V2. Okay, now refer all the quantities in primary side. Okay, now refer or transfer all the quantities in primary side. This is R2 dash, that is resistance R2 transfers in the primary side. Okay, this is R2 dash. Similarly, this is X2 dash, and this is ZL dash. Wait a minute. Hello. So these are the quantities if you refer into the primary side. Achha. Just see that E2 dash equal to E1. Since E2 dash equal to E1, we can connect the primary side with the secondary side. Go to previous page. If you transfer this whole circuit in primary side, then what will happen? E2 becomes E2 dash, which is equal to E1. Since here is E1 and here is also E1, we can connect the two terminals. Okay, so what will happen? We can connect these 2 points and connect these 2 points. Condition is that if we transfer all the secondary quantities in primary side. So this is the secondary side, this is the transfer parameters, and this is your connections. Okay, nothing but this, what we have discussed. This is R1, X1, this portion is known to you, and this is E1. Since for secondary side, it was E1, so we can connect the 2 points. 2 points, and another remaining same, that is R2 dash, X2 dash, ZL dash. Okay, I think this is clear to you. So this is the equivalent circuit of transformer. Okay, since I2 is negligibly small and it is the 2 to 3% of the full load current, so we can transfer these portions into input side. We can transfer these portions into input side. This is for the sake of simplicity, for tackling problem or calculating, solving problems. Okay, and if we shift these portions in input side, then it is known as the approximate equivalent circuit. This is the approximate equivalent circuit. So this is the exact equivalent circuit, and this is the approximate equivalent circuit. Okay, so this is your approximate equivalent circuit. Okay, sometimes it can also be avoided. If we avoid this, it becomes to more approximate equivalent circuit. Okay? What circuit you will consider, it depends on you. Okay, that is perfection. What perfections you want for performing calculation, etc., etc. Now we can repeat this. Topic was equivalent circuit, and this is the circuit you know, ideal transformer, because there is no resistance and leakage reactance. If you consider this, it comes into this figure. So the inner portion, that is two coils, is the ideal transformers, and these are R1 X1 and R2 X2 is connected for getting the practical transformers. Apply voltage V1, it will give you current I1. It has two portions, I0 and I2 dash. I2 dash is supply the load current, and this is the magnetizing component. This is the exciting current. It has two components, I mu and I omega. I mu for reactive magnetizing current, magnetizing portion, magnetizing component, and this is loss component. Okay, R0 equal to U1 by I omega, and X0 equal to U1 by I mu. Okay, so this is the primary circuit, and this is the secondary circuit, and this is the isolation, isolated by two coils, primary and secondary. This was the secondary coil. This is your transfer. If you transfer all the quantities from secondary side to primary side, it will give you this one. Okay, from here we see that this voltage is E1. Since for primary side, the voltage induced EMF across the coil is E1, and here is also E1. We can connect these two, provided we transfer all the quantities in primary side. Since both voltage are same, so we can get this circuit where these 2 points and these 2 points are connected. Okay, so this will give you the exact equivalent circuit. For the sake of simplicity, we can transfer this portion here, these portions here. If you transfer these portions here, then it becomes approximate equivalent circuit. And this is the more approximate equivalent circuits where exciting current is there. Note that you can consider any of the equivalent circuit that is exact, approximate, or more approximate, depending on your requirement. Okay, now the transformer test. Transformer test means what? We have to find out all the quantities, all the equivalent circuit quantities. Okay, what was this? R0, X0, R1, R2 dash, X1, X2, etc., etc. Okay, now two tests are there. One is short circuit test, another is the this will be an open circuit tests. Okay, this is not short circuit test. This is open circuit test or no load tests. Two tests are there: open circuit test and short circuit test. Now first come to open circuit test, from where we get the exciting circuit parameters. Okay, so this is your transformers. You know, two coils are there. One is primary and another is secondary. You can perform your experiment in any winding. Okay, any winding. But convention is that you have to perform open circuit test in low voltage winding, and high voltage winding remains open. Once again, there are two coils. One is primary, another is secondary. And suppose it is low voltage coil and this is high voltage coil. Okay, since it is open circuit, so load is not connected, load is disconnected. In this case, E2 equal to V2. Okay, in primary side is low voltage side, you have to apply voltage here. Okay, scan the circuit with a voltmeter. It will give you the voltage reading. This is ammeter. It will give you the current reading. This is wattmeter. You know wattmeter, it measures the power. Okay, wattmeter, it measures the power. It has two coils. One is current coil, another is pressure coil. This is the current coil and this is pressure coil. Common point is there. The current coil CC and this is PC or pressure coil. It will give you the wattage what is consumed or what is input, which is equal to Vi cos theta. Okay, the real power. It will give you the real power. Now connect the circuits with the auto transformers. You know the auto transformer of Variac. You have to provide the full rated voltage. That is V1 is the rated voltage. So apply rated input voltage, and at that time the record I0, W and A. Sorry, voltage, power and current. You have to record voltage, current and power, and these are for no load tests. Okay, these are for no load tests. Since current flow is very low, that is minimum, because load is disconnected, only I0 is flowing, we can avoid this. We can neglect this, and we can consider this input power is supplying core loss. So W will give you the core loss. W will give you the core loss, and this is the expressions. W equal to V1 I0 cos phi 0. Okay, V1 is the applied voltage, I0 exciting current, cos phi is the power factor angle. Okay, so cos phi equal to W by V1 by I0. You know I0, so I mu equal to I0 sin phi 0. IW or I omega equal to I0 cos phi 0. So exciting current two components you can find out, I mu and I omega. X0 equal to V1 by I mu, I0 equal to V1 by I omega. Okay, here you consider E1 very nearly equal to V1. Okay, that's why we can write this. So these are all the approximates were very near to the data, very near to the manufacturing data, etc. So we can gist this transformer test. This is required for finding or calculating all the parameters, equivalent circuit parameters. Two tests are there: open circuit test, known as the no load test, and there is the short circuit test. Okay, this is circuit diagram, primary and secondary, low voltage side and high voltage side. Generally, we are performing open circuit test in low voltage side, while we perform the short circuit test in high voltage side. Okay, now apply voltage V1 here. Apply voltage V1 here and record all the quantities V, W and I. Okay, and from these three readings we can find out X0 and R0. So the among the parameters R0 and X0 can be find out. Okay, I mentioned that the input power supplying core loss. The core loss consists of two parts, two portions, two parts. One is hysteresis loss and another is eddy current loss. You know the hysteresis loss and eddy current loss. Now, how we can separate this? Separations of losses. Total core loss W1 equal to A plus B F square. You know what is A and what is B. Actually, these come from Steenmar's empirical relations. Okay, Steenmar's empirical relations. You know that the hysteresis loss depends on the frequency and eddy current loss depends on the frequency square. Okay, frequency square. From here we can write W1 by F equal to A plus AB. Okay, now for the circuits, this is connected with the Variac to adjusting voltage or providing different voltage with different frequency. Now change the frequency and calculate and take the readings of W1. You can get a set of relations, and now draw the curve F along x-axis and W1 by F along the y-axis. Okay, so you get the portions, this straight line. Okay, Now you can extrapolate this. Now we can extrapolate this. Okay, now we can extrapolate this. Okay, see that when f equal to 0, it will give you A. So this portion is A. This portion is A. And another portion is B. Another portion is B. Okay. However, you can calculate the two losses. One is AF, another is BF square. Okay, I think it is clear to you. Once again, the W1 supplies input power, which is input power, which supplies the core loss. You know, the core loss may be two types. One is the eddy current loss, hysteresis loss, another is the eddy current loss. Hysteresis loss depends on the F, proportional to F, and eddy current loss depends on the F square. So we can write W1 equal to A plus B F square. From here we can write W1 by F equal to A plus B F, A plus B F. Now change the frequency of input and take a set of readings. Take a set of readings from where you draw the curve F along x-axis and W1 by V along y-axis. You get these portions. Now extrapolate this. Okay. Now extrapolate this. From here, you get the value of A, which is these portions, and value of B. Obviously, value of B depends on the frequency. What frequency is there? Okay, it changes with the frequency. However, you get the value of A and B from where you can get core loss for any frequency. Okay, core loss, portion of the core loss at any frequency. Now come to short circuit test. This is just a reverse. That is, you have to apply voltage in high voltage side. Voltage in high voltage side, and the secondary side it's short circuited. Once again, from where you can get the voltage ratio only. To get this, you have to connect a voltmeter here. Okay, from here you can get the K, the value of K or turn ratio. Anyway, short circuit test, apply voltage in high voltage sides. Connections are shown here: the ammeter, wattmeter, and voltmeter. This is the supply, and it is connected with the variac. And secondary, short circuited. Now, adjust the voltage such that the rated current will flow. Okay. In open circuit test, you have to apply the rated voltage, but here you have to apply the rated current instead of rated voltage. Okay. Obviously, the voltage responsible for flowing rated current in short circuit condition is 10 to 15% of the rated voltage. Okay, so this is very minimum. Since the voltage is low, current is a maximum of rated, so the wattmeter will give you the copper loss. And here we can neglect the core loss. Okay. Now the Z01, that is the impedance referred to the primary side. You know, all the readings are in primary side. So Z01 equal to VSC by I1. VSC is the short circuit voltage and I1 is the rated current. So Z01 VSC by I1. W equal to I1 square by R01. So R01 equal to W by I1 square. So X01 equal to this. So we can get the parameters, all the parameters. Okay. Again, you can separate R1 and R2. How it is possible? You have to measure the resistance of one coil. If you measure this, then you can separate R1 and R2, etc. However, our aim is to find out the R01 or X01 or R02 or X02. Once again, we can repeat this. Transformer test, two tests are there. One is open circuit test, another is short circuit test. This is your open circuit test. You have to apply voltage in low voltage side. Okay, and this is the formula. This is the relations from where you can get R0 and X0. Okay, then you can separate the losses. What is the eddy current loss and what is the hysteresis loss at any specified frequency. Then go to the short circuit tests. Here you have to apply voltage, obviously reduced voltage in high voltage side, and take all the readings, and from here you can calculate the parameters. Okay, আচ্ছা এই পর্যন্ত থাক, হ্যালো,
Yes, sir.
হ্যাঁ স্যার থাক
আচ্ছা থাক, আচ্ছা মোটামুটি বোঝা